All right, I'm going to go through protein synthesis and do some problems out of product chapter 22 again. First, I want to go through the steps for your protein synthesis. All right, you have your transcription. That's when your messenger RNA is formed from a DNA strand. All right, so then your transfer RNA molecule in translation is going to bring in the correct amino acid from the codon on your messenger RNA. The transfer RNA has the anticodon to match the codon in your messenger RNA. You're going to have a chart, a codon chart, which is based on your messenger RNA, and that will tell you which amino acid that transfer RNA is going to bring in. All right, so transcription, you're going to have some DNA that's going to unwind, and you're going to use that DNA as a template. The messenger RNA is then synthesized using your complementary base pairing. Remember, uracil is in RNA, not in DNA, and thymine is in DNA, not in RNA. So that is the only difference. So you're going to have your DNA. You have to know your base pairs. G goes to C and T goes to A. When you're looking at RNA, it is the same, except you have U instead of T. So it's still base pair GC, but now it is U going to A. There is no thymine in RNA. All right, and so here is the DNA, the double helix. All right, and so you're going to synthesize your messenger RNA. All right, that is going to take your messenger RNA. Well, here is your DNA strand. So the messenger RNA is going to then, of course, with your messenger RNA, you have your base pairs, GC, and then UA. All right. So again, remember that this is DNA. Anytime you see a T, you know that you're looking at DNA. If you have a U, you know you're looking at RNA. And so if it says what sequence of bases are in messenger RNA, well, you can eliminate this and you can eliminate that, and there's only one answer it can be, because when you do messenger RNA, you cannot have thymine. So this is going to be your GAUUCC, which is right here. So when you're multiple choice and there's only one that could possibly be in RNA, that would be a very easy multiple choice question. All right, so now this is your DNA, so this is your messenger RNA. So now you've got, in this case, we have two codons in this messenger RNA. We have GAU and we have UCC. This is messenger RNA. This is where the codons are at. All right, and so when your transfer RNA comes in, it's going to come in with the anticodons. So your transfer RNA, and there is not a anticodon chart. The chart is a codon chart. So this is the codons. The transfer RNA has the anticodon. All right, so the transfer RNA is going to have the CUA, the anticodon, and the transfer RNA is going to have the AGG anticodons. All right, so your transfer RNA also has the anticodons, and it brings in the correct amino acid. All right, and so you have, again, this is your messenger RNA codons. These are not the transfer RNA anticodons. This is your codon chart. This is going to be given. And so if you have your codons, if we go back and we can, all right, codons GAU, so we can look at GAU. All right, so your first letter is G, your second letter is A. All right, and so GAU, that's ASP. All you have to do is find the three letters. You do not have to know what ASP stands for. You just have to then find ASP. That's your first amino acid. All right, and then you have your second one, which is UCC. And so then you find on your codon UC. All right, so UCC, and that is SER. Again, you do not have to know what SER stands for, but you would have your two amino acids would be ASP, then to SER. That would be, and then this bond here is your peptide bond to connect your amino acids. All right, so you will be given a DNA, you have to make the messenger RNA, and then you have to make your amino acids. Again, given this chart, if it was that would have been the problem, and your answer is right here. It should be quite simple to go from a DNA strand to a messenger RNA strand to your amino acid combination. All right, so anyway, again, you just look these up. This is a messenger. The key is messenger. The only ones that mess this up is they use a transfer RNA instead of a messenger RNA. You're getting your codons from a messenger RNA, not the codons. It's a codon chart, not an anticodon chart. All right, you just look them up, and then you just write them in order. PRO, SER, GLY, LEU. That is your answer. All right, so again, not much of a check here, but anyway, this is your messenger RNA. You just find GCC, right? GCC, alanine. GUA, you find GUA, valine. You find GAC, you find GAC, you got aspartic acid. Not sure how you would miss that problem, but anyway. So there will be a question on that. It should be an easy question. Many people miss it. I don't know why. Make sure you can go from a DNA to a messenger RNA. You have your base, your triplet codons. You go to the codon chart and you have your abbreviation for your amino acid, and that is how you work that problem. More problems out of chapter 22. All right. All right, so your alpha amino acid. All right, so you have to know what an alpha amino acid means. So you have your acid, and off of your alpha carbon, the carbon connected to the C double bond O is your alpha carbon. You have an amine group, which is an NH2. All right, and this carbon has an H and it has an R. So here is a generic alpha amino acid. The NH2 is the amino group. Your carboxylic acid is a C double bond OOH. So here is why it's called an acid, and here is why it's called an amino. And alpha is because this carbon is called the alpha carbon. The carbon that is adjacent to the C double bond O is the alpha carbon. And so you have off of the alpha carbon, you have an amino group. So it's an alpha amino acid. And there are 20 different R groups for the 20 main amino acids. There's more than 20, but the 20 make up most of our proteins. And so we stick with the 20 alpha amino acids. All right. You have to know whether your R group is polar or non-polar. You don't have to memorize all the names, but if I put alanine and I say that the R group is equal to CH3, and I want to know if that R group is polar or non-polar, if it is only carbons and hydrogens, then of course it is a non-polar side chain for that amino acid. All right, if it contains an oxygen, if your R group contains an oxygen and anything else, if there's an oxygen in it, it's polar. Doesn't matter what else is in there. If there is one oxygen, it is a polar molecule. go chapter 4. So we're just some amino acids, all right? But you have to know if it's polar or non-polar if your side chain has a carboxylic acid. There are two of them that have a carboxylic acid. These would be the acidic amino acids. If you have amines, NH2 groups, these are going to be your basic. So if your R contains an NH2 group, it's going to be basic. So there are 3 basic amino acids. There are 2 acidic amino acids. So you should know the 2 acidic amino acids and the 3 basic amino acids. And you can memorize them, or just you're looking for an amine group, because it's going to give you the R group. Here's the R group. If the R group has an amine group, then it's basic. If the R group has a carboxylic acid group, then it's going to be acidic. And we're talking about the R groups. Every amino acid has a carboxylic acid group and an amine group. So they all have that. It's just the R group. Does the R group add another amino group? Does the R group add another carboxylic acid group? If it does, if it's carboxylic acid, it's acidic. If it's an amino group, then it's basic. All right, so let's go to our chapter 22. All right, so 2230, what was our first problem? 2236. 2236. All right, for complexes shown, we have MF6 minus 3. We have M just means metal. And we have MCN6 minus 3. We have a metal F6 minus 4. And we have a metal CN6 minus 4. All right, so these complexes, which would have the d electron distribution shown as diagram below. All right, note that the neutral metal atom in each complex is the same. All right, so M is the same neutral metal complex, and so they're giving it as, they show the electron distribution, so they have it shown this way. All right, so here, if you have an F6, a minus 3, we know this is a minus 6 for the 6 Fs. In order for this to be a minus 3, we have to have a metal that is plus 3. A plus 3, a minus 6 gives a minus 3. All right, same thing here. You're going to have Cn, that's minus 6. This metal is going to be a metal that has to be a plus 3 to give an overall of minus 3. If you go over here, your minus 6, you got to have a plus 2 to get a minus 4. Again, minus 6, you need a plus 2 to get a minus 4. All right, so for this, you should see that you have 1, 2, 3, 4, 5, 6. So this is a D6. All right, and not only should you see that this is a D6, you should also see that this is, of course, an octahedral splitting pattern. And that doesn't eliminate any of these. These all have 6 coordination number. Every one of these is an octahedral complex. All right, so we need a D6 octahedral, and you also see how they were put in. And they were put in as a high spin. All right, and so when you see that it's a high spin, we know that we're going to have weak field ligands. All right, and so we can eliminate the cyanides. Cyanides are strong field ligands. All right, so the metal that we are looking at here, they tell us the electron configuration of the metal. The neutral metal is argon, and that is a 4s2 3d6. All right, so they tell us, they don't tell us the metal, although we just go right to the periodic table and we find our 4s2 3d6, and we know that we're looking at iron. They don't tell us the identity of the metal, but the electron configuration would give us the answer to that. All right, so we want to know, all we need to know is if we have a d6 or not. So if you had a metal that's +3 here, so we got rid of our 3 electrons, the 2 S's and 1 of the D's, this would be a D5. So this metal +3 is D5. Well, we are showing 6 electrons here, so that is not the answer. So it had better be this one, because by process of elimination so far, it's the only one that can be the answer. Here we have a metal that is +2. We get rid of the 4s2. We have a D6. We have weak field ligands. We have a high spin. So that is the answer. It is an MF6 minus 4. That would be a D6, and that would be a high spin for the octahedral. All right, next one was 2238. Find the oxidation numbers of the transition metal in each of the following compounds. COSO4 sub 2. No, just COSO4. All right, so you know sulfate, SO4 is -2. And so cobalt has to be +2. So you have cobalt that is +2. And while we're doing it, a cobalt 2, you find cobalt on your periodic table. All right, and so your cobalt is element number 27. And above that, you see the number 9, and so cobalt 2 is D7. And if you have a Ta05, all right, Ta2O5, so this is a -2 for each oxygen, so that is a -10, so this has to be a +10 because it is overall neutral, and so your Ta is an oxidation of 5. So you find Ta on your periodic table, and it is element number 73. You look at the number on the top of that column, and it is a 5, and so a Ta5 is a D0, which indicates that this would be either a white or colorless compound, because it doesn't have any d electrons for D to D transitions. All right, here you have your Cu. You've got OH3Cl, Cu2, OH sub 3, and Cl. All right, so as ligands, we know that the chloro ligand is a 2 minus 1. We know that the hydroxyl ligand is also a 2 minus 1, but there are 3 of them, so that is a 6 minus 3. And so we know that we're going to have a +4 for the 2 Cus. And so both of these Cus are copper 2. And when we look at the periodic table, we find copper number 29. The number above the copper is 11. And so a copper 2 is a D9. All right, 42. 22.42. Give the coordination number of the transition element in each of the following complexes. All right, so we've got a nickel. We have an NH3 sub 6. And then a bracket. And then we have a ClO3 sub 2. All right, so the name, we'll name it, it is a hexamine, 2 A's or 1 A, hexamine. Now nickel. Now the nickel, though, we have to find the oxidation. So back to first semester, we had memorized ClO3 minus was chlorate. All right, so we know that this is going to be a total of a -2, so this complex has to be a +2 complex, and so we are nickel 2. And so this is hexamine nickel 2 chlorate. All right, so nickel 2, you find nickel on the periodic table. The element is, where's my nickel? Right there, it's number 28, and so it's 10 above that, so that's D8. All right, and then you have your 6 NH3 ligands plus your 12. All right, and so this is a 20 electron complex as written. Again, you would not predict that to be stable. You only predict 18 and 16 to be stable. This would be a 20 electron complex. All right, we have a coordination number is equal to 6. So this is octahedral. These are strong field ligands. And so this is going to be a low spin. Now, it doesn't matter because we have a D8. And when you have a D8, even low spin or high spin would give you the exact same electrons. You would put them in differently, but when you are done, you would have the exact same electron configuration for putting in 8 electrons. All right, and so since we have an electron up here, one or more electron up here, the hybridization is sp3d2. All right, part B. Part B is Cu NH3 sub 4 SO4. All right, so we know SO4 is -2, so this has to be a +2. And so you have tetraamine, copper 2, sulfate. All right, so the sulfate is just a counter ion, so your coordination number is equal to 4. So now when we look at our copper 2, we already did a copper 2 before, a copper 2, 11 is above the copper, so copper 2 is D9, and so it is not D8. If you have a coordination number of 4 and you are not D8, then you are always going to be tetrahedral. And then if you're putting in the electrons, you have the reverse of your octahedral. You have 2 on the bottom and 3 on top. Every tetrahedral is a high spin. And so you have your 9 D electrons that go in. And your hybridization for tetrahedral is sp3. Part C is Cr. This one is interesting. CrEn sub 3. Cl3. All right, so this one, then we can do our total electron count. So our total electron count is our D9 plus our 8 for the 4 coordinated NH3s. This is a 17 electron complex. Again, we would not predict that to be stable. We only predict 16 and 18, but that is a stable compound. All right, so we have Cl3, so that's our chloride. So this is going to be 3 minus 1, so this has to be a +3. Ethylene diamine is neutral. And so we have tris, ethylene diamine, chromium 3 chloride. All right, and so our coordination number is not 3 because you have to know that ethylene diamine has in one ethylene diamine, it has a coordination number of 2. So your coordination number is 6 because we have 3 of them, and this is octahedral. All right, and so when you have your chromium 3, and you find chromium, which is number 24, the number above that is 6. So chromium 3 is D3 plus each En is a 4 electron neutral, so plus 12 for the 3 of them. This is a 15 electron complex. All right, and so when you put in your En, these are strong field ligands. And so this is going to be low spin. So when you put in your D3, again, it wouldn't matter if it's high spin or low spin. If you only have 3 electrons, the first 3 go in the same. All right, and so now this one is empty, and so it's a D2 sp3 for the hybridization of that octahedral. And then the last one is a K2 NiCN sub 4. All right, so this, you always have to name the cation first, so that's potassium. And then you have a tetracyano. And now you got to find the oxidation of your nickel. All right, so 2 potassiums, that's a +2. That means that this complex is a -2. Cn is a 2 minus 1, so this is -4. So your nickel has to be a +2. And now it's part of the anion, and so it is not nickel, it is nickelate. So that is tetracyanonickelate 2. So it is potassium tetracyanonickelate 2. And now we have nickel 2. Nickel 2 is the 10 is above it, it's a D8. So now we have a coordination number equal to 4, and now we have a D8. So now we are square planar. And so your splitting pattern for square planar is 2, 1, 1, and 1. And every square planar is low spin. And your Cn minus is a strong field ligand. That doesn't make it low spin. Square planar makes it low spin. It wouldn't make any difference if your ligands were strong or weak field ligands. All right, and so every time you do square planar, this orbital will be empty. That is one of your d orbitals. And so dsp2 is the hybridization for your square planar. (2244). For each of the following complexes, determine the oxidation state. All right, so just asking for the oxidation state. You got your CO, you've got your Cl, you've got your En2, you got your NO2, and then a bracket, and then an NO2 again. All right, so you have chloro. That is a 2 minus 1. You have ethylene diamine. That is a 4, 0, but you have 2 of them, so that is an 8, 0. All right, and so NO2, remember NO3 minus was memorized as nitrate. So NO2 minus is nitrite. All right, and so, but that is a negative ion, so it is nitrito. So this is nitrite O. Drop the E and you add O. But here it is simply nitrite, because outside the bracket you are not a ligand. And so this one again is very difficult because ethylene diamine takes up 2 coordinations. So that's a coordination number of 4 for the 2 ethylene diamines, plus 1 for the chlorine, and 1 for the NO2. So your coordination number is 6. This is octahedral. So your NO2 is minus, so this is a plus. And so your nitrito, it's O because it's a 2 minus 1. All right, and so you got your minus 1, you got your 0, you got your minus 1. The cobalt has to be a plus 3 in order for that to be an overall of a plus 1. And so your cobalt is oxidation number of 3, and your cobalt 3, you look at cobalt, and the number above your cobalt is 9. Cobalt 3 is D6. All right, and you have a weak field ligand, you have a strong field ligand, you have a strong field ligand. You only need one strong field ligand to make this low spin. And so when you put in your 6 electrons, they all are at the bottom, low spin. And so this is a D2sp3. And if you were to name it in alphabetical order, you've got chloro, bis, ethylene, diamine, not di, since it has di in the name, you use bis for 2 of them. And then you have nitrito, cobalt 3. And then nitrite. All right, the next one is PtCl4 minus 2. All right, so that's part of the anion. So this is a tetra chloro platinate 2. And it's 2 because your chlorine is going to be a 2 minus 1, so that's minus 4. This has to be a plus 2 in order to give an overall charge of minus 2. All right, and so your platinum 2, you find platinum on the periodic table. The number above top of the column of platinum is 10. So platinum 2 is D8. Coordination number is 4. This is square planar. 16 electron complex, DSP2. We didn't do the electron count up here. We just add them up. You got your 6. So this is D6 plus 2 is 8, plus 8 is 16, plus 2, 18 electron complex. This is an 18 electron complex. K3, CrCN6. So this is potassium, hexacyano, chromium. So that's a minus 6. 3 Ks is a plus 3. Overall, it's neutral, so your chromium has to be a plus 3, chromium 3. Except, since you have the plus 3 here, and this is the minus 3, it's not chromium, it's chromate. Again, when it's part of the anion, the metal has to end in ATE. All right, and so your coordination number is 6. You are octahedral. All right, and chromium 3. You look at the periodic table, you find chromium, number 24, number above it is 6, that's a D3, plus the 12 electrons that you get from the 6 CNs. This is a 15 electron complex. All right, and so since CN, these are strong field ligands, and again, it doesn't matter because it's D3. You put in the 3 electrons as low spin. All right, and so this is D2sp3 for the hybridization of that octahedral. All right, then the last one on 44, we've got a iron, H2O sub 5, and OH, and overall it is a +2 charge. All right, so water is just neutral to 0. Hydroxo is a 2 minus 1. In order to get a +3, your iron has to be a +3. A +3 minus 1 is a overall of +2. So we have iron 3. You find iron on the periodic table. Number 26. The number above it is 8. That is a D5. All right, and you would have 5 waters, so you would add 10 for the 5 waters. You would add 2 for the 1 OH. Our total electron count is a 17 electron complex. We have 5 waters and 1 OH, so our coordination number is equal to 6. It is octahedral. These are all weak field ligands. All right, and so since we have all weak field ligands, then we have a high spin. And so when we put in our 5 electrons, they go high spin. And we have 5 unpaired electrons. And then since those are occupied up there, it is sp3d2 for the hybridization. And that is penta, aqua, hydroxo, iron 3. So it is penta, aqua, hydroxo, iron 3 for the name. Yeah, right. So this would be, anytime you have an unpaired, it's going to be a paramagnetic, yes. Because it's occupied. If it is a D3, regardless of high or low spin, if these are empty, it's going to be D2sp3. But again, most high spins are going to be sp3d2. But if you have a high spin with 3 or less d electrons, then it would be the D2sp3, which again is rare. But you pretty much only would see that. There's other compounds, but you do see that. Just it's not very common. All right, 46. Consider Mn, NH3 sub 2, H2O sub 3, OH, and +2. All right, so we have diamine, we have Fri-aqua, and we have hydroxo. All right. So diamine alphabetically is going to come first. It's about the amine versus the aqua. So do it in alphabetical order. Diamine, tri-aqua, hydroxo, and then manganese. Okay, this is a -1. That's 0. That's 0. This has to be +3. Manganese 3. All right, so the oxidation is Mn3. I'll put it as a Roman numeral. Mn, periodic table number 25. The number above the Mn is 7. So that is a D4. 4. 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 - 4 All right, and so our coordination number, we have 2 here, we have 3 there, we have 1 there. Coordination number is equal to 6. That makes it octahedral. We have a strong field ligand. The NH3 is a strong field. Water is weak field. OH is weak field. But you only need 1 or more strong field ligand in order for it to be a low spin. All right, and so when you put in your 4 electrons, it is low spin. And so now it is D2sp3 because the 2 on top are empty. You have 2 unpaired electrons, paramagnetic. All right, so they're saying if our Mn is a +3, what would the charge on the complex be if the Cl, if they all 6 were Cls? Then the charge on the complex would be a -3. What would the charge on the complex if all ligands were chloride ions? Okay. So it's a little, I'll take that as we're keeping the oxidation of the Mn, the +3, and now we have 6 chlorines, and so the overall charge of that complex would be a -3, and then that would be named as a hexachloro. Manganate 3. That is a Roman numeral 3. 8 because now it is an anion. Manganese up there because the overall was a positive. So you just give the name of the metal if it's neutral or positive. The metal has to end in ATE if it has an overall negative charge. All right, 2248. Name the following complexes. All right, so we have K4, MOCN6, all right, so potassium is +1, so that's +4. CN is -1, so that is -6. So your MO is +2. So you have potassium, hexacyano, molybdate, 2. 8, molybdate, because this is a -4 because this is a +4. Your coordination number is equal to 6. Potassium, sodium, those are never ligands. And there is a bracket. Anything that is outside the bracket, if there's a bracket, are not ligands. All right, so you have MO, you find them on your periodic table. It is number 42. The number above it is a 6. And so you have MO2, which is D4. We have a strong field ligand, so that means it's low spin. And so when we put in our 4 electrons, they are all 4 at the bottom. And again, it is paramagnetic with 2 unpaired electrons, D2sp3, same as the last one that we did. All right, we have a Cu NH3 sub 2, H2O sub 2, and then a +2. All right, so we have diamine, diaqua, and that's 0, and that's 0, so the copper has to be +2, copper 2. All right, coordination number is 4. All right, and so when you do a copper 2, the number above copper is 11, so copper 2 is D9, not D8. That means it is tetrahedral. All right, so then you have 2 on bottom, 3 on top, and then you put in your tetrahedral, which has 9 electrons. This is a strong field ligand. This is a weak field ligand. That doesn't make any difference. Tetrahedral is always high spin. And it is paramagnetic with 1 unpaired electron. Well, that was not the right number. Okay. So that was supposed to be 48. Oh, that was 48. It was this. I did part B on 47. All right. That was 47B. All right. So 48B, the one we're supposed to be doing, is CrF6 minus 3. All right. So that is hexafluoro chromate 3. And how did I get 3? Well, I got 3 because F is minus 1, so that's minus 6. Chromium has to be plus 3 in order to give an overall of minus 3. All right, so your coordination number is 6. It's octahedral. And Cr3, chromium's number 24. The number above that is 6, so that's D3. So that's a weak field ligand. All right, so this is high spin. And so here is an example of a high spin that is going to only have 3 d electrons. So this is a D2sp3. Again, rare for a high spin, but if you have a high spin with D3 or less, then these two will be empty. In order for this to be full, you have to have at least, or to have anything in it, has to have at least 4 electrons. All right, again, chrome 8 has to end in 8 here because it is part of the anion. All right, B, C2O4, sub 3, minus 2. So it's vanadium, so it's vanadiate. Yeah, anyway, it has to end in 8 because it is negative 2. And this is the oxalic acid, so it's oxalate. All right, but as a ligand, it ends in O. That is oxalato. And so this is a tri-oxalato. Vanadate, vanadium 8. And so now this one is difficult because your oxalato is a C double bond O, C double bond O, then the O, and then the O. And so it is going to connect on both ends. So this is a going to connect in 2 different spots. And so your coordination number here is 6, and it is octahedral. And then the last one on 48, you got your K2, FeCl4. You've got your potassium, tetrachloro, ferrate, and that's 2. And it's 2 because you got minus 4, you got plus 2. So to be neutral, that has to be plus 2. And when you do iron 2, you find iron. The number above iron is 8. That is a D6. Coordination number is 4. And so that is a tetrahedral. The only time you're going to predict a coordination number 4 to be square planar is if you have a D8 and not a D6. All right, we will do more problems tomorrow. I'm gonna post all these as well